Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 14 on cluster analysis. Cluster analysis is a multivariate exploratory tool for locating and grouping observations that are similar to each other across features. So, in contrast to discriminant analysis, which we'll cover in the next chapter, where we actually know what groups we have and we're trying to define a rule to distinguish them for classification later on, cluster analysis defines what the groups are by similarity. And it's often up to us to look at the groupings that cluster analysis revealed and make sense of that. There are tons of clustering algorithms out there. If you want to look at some of the ones that are implemented inside R, you can look at the footnote here. We're going to focus on some of the simple methods in this chapter called agglomerative hierarchical clustering methods, where you basically start where every observation is an individual point, and then based on how close points are, they group together. And so your cluster sizes build and build and build until you end up with one big cluster at the end. So you can think of maybe like water droplets binding together and forming these larger and larger groups. So I'm going to show you an illustration, and these steps sort of narrate what ends up happening. But I'm going to start off with some fake data. I've got two variables, x1 and x2, and that's just so that we can plot the data. And I'm using the text option to read this table in directly from text, and I'm going to put that into intro for the introductory example for cluster analysis. So here's our data frame. We've got x1 and x2. No surprises there. I'm going to actually also do principal components here and use both x1 and x2 as the features, and this will effectively perform a rotation of the data in intro.pca, and it won't actually matter which of the original data or the principal components that we use in this case for clustering, though many in the clustering plotting algorithms, or plustering the clustering plotting functions are going to often print or plot the first two principal components. Unique New York, red leather, yellow leather. All right, so here's a plot of the original data. So we got x1, x2, and here on the right is the principal components. And you can see that the principal components are effectively just a 180-degree rotation of the original data. The observations 5, 6, and 8 are in the lower right here and in the upper left here. Okay, no big deal. So we're going to first look at the code. Actually, let me come back to the code. I'm going to scroll down and show you what happens in clustering. We start off with 8 observations, 1, 2, 3, 4, 5, 6, 7, 8 points. And clustering is going to join the closest sets of points by some distance metric, and we're going to talk about 3 distance metrics in a moment. But generally speaking, it's going to find the 2 closest, and then it's going to join them together. So now observations 6 and 8 have joined together to make cluster 6. So these colored numbers, 1, 2, 3, 4, 5, 6, and 7 are the 7 clusters after joining the first 2 points. Then we're going to work to the right, and the next 2 closest points are the numbers 1 and 2. So those get joined together, and now we have only 6 points. Then the next sets of closest points are 2 and 3, which get joined here. Then the next sets of points is that this 3 is now closest to these 2 points here. So those 3 points get clustered here. Then these two pairs of points, so these two clusters, will get joined into a single cluster here. And then finally, this last point down here is closest to these three, so it gets joined on. And then the obvious last step is that these two clusters get joined into one big group. So to show you how I made all those plots, I think below I want to show you one thing first. So here is the original data intro, and dist creates a distance metric between all the points. It effectively measures the Euclidean distance between all the points. Basically, if you took a ruler and stretched it out between one point and another in whatever dimensional space you're in, and draw the distance of that straight line, that is the distance here. So I'm putting that into intro.dist. So right, it's the intro dataset. Distance is the operation that I just did. And unfortunately there's a bad page break here, but there's actually seven columns here. And for example, this number 2.8 is the distance between observation 1 and 2. And so you can look through all these distance values. Here's the last one between 7 and 8. And one way to do clustering is just to search through all this and find the smallest numbers. And it looks like it might be this one. This happens to be the distance between observations 6 and 8. And if we scroll up to the previous page, we see that those are the two observations down here that were grouped first. All right, let's look at the code that created all of that. The first operation was to calculate the distance matrix and put it into intro.dist. Then the hclust function performs hierarchical clustering, and it uses the distance matrix that was calculated, and then we also specify a method for determining what close means, so the distance between clusters. And in the next section we'll look at three versions. Average is one of those methods, and we'll assign that hierarchical clustering to intro.hc for hierarchical clustering, and average is the method that we used. These two lines just specify that we're making some margin space in the plot that comes next, and then at the end we reset the original plot options. But this is the code that we want to look at for creating those 6 plots. In the cluster package, I'm going to ask for a cluster plot of the intro data, and the number of clusters that I'm going to use based on the average hierarchical clustering object up here. K is going to specify the number of clusters that are going to be printed. And then I've got a bunch of options, big deal. The I-clus, the number of clusters, are going to start at 7 and then go down to 2. So that when we look at these plots, I start at 7 clusters, then 6, then 5, then 4, and I'm plotting every step of the way the clusters that are formed. So that is the logic of all of this. So we needed to calculate the distance of the data set in order to use the hierarchical clustering, and then we used the hierarchical clustering object in this function cut tree, which is effectively, we'll look at dendrograms, or these trees, in a moment, but this helps us decide which observations belong to which clusters when we look at 4 clusters or 5 clusters or so on. And the clus plot plots the original data with those groupings. All right. If we look at the dendrograms, and I'm going to use now the 3 different methods of measurements, and then I'm going to define them later. Here's single, complete, and average. And if you simply plot the hierarchical clustering object, it will give us what's called a dendrogram. It's a tree where the terminal nodes are each observation, and then as you move from the bottom upwards, there's a height. And the height is a measurement of the distance between the clusters. So we saw before that observations 6 and 8 were grouped together first, and you can see that they join, these two branches of the tree join lowest on the height because they were the closest. Then we ask what's the next closest, and I think we joined we did average linkage in the example above. So let's see, so 6 and 8 were joined first, and then 1 and 2 were joined, and then 3 and 4 were joined, then 5 joined the group with 6 and 8, then these two pairs, 1, 2, 3, 4, were joined all together, then observation 7 joined this group with 5, 6, and 8, and then finally they're all joined together. So working from the bottom, we've got all the individual observations as separate clusters. At the very top, all the observations are joined into a single cluster, and then depending on where we draw a horizontal line in the middle, we get some number of clusters. So just for simplicity, if I draw a horizontal line at 10, that breaks my data into 2 clusters. Basically, imagine snipping these branches and I get clumps of leaves, 2 clumps of leaves. And so you can see that the average distance method has a slightly different tree than complete and single. Single is perhaps the most different. In fact, complete and average has the basic same shape in the 2 trees. Single looks quite a bit different, however. Let's see, is that true? 6, 8, the leaves at the bottom are arranged differently, and the pattern is quite similar. I think the order that these are joined are different. In fact, 5 joins 6 and 8 here, whereas 3 and 4, it takes a little bit longer to join 3 and 4, whereas down here 3 and 4 joined before 5 joined 6 and 8. So the ordering is a little bit different. We will see an example at the end of this chapter where it makes a huge difference which metric you use. So it's important to be aware of the characteristics that each of these have, and that you can get different results. So we'll talk about distance measures now, the single, complete, and average. And I think it's easiest perhaps to define this from a picture. So imagine we've got this set of 5 points, and we want to measure the distance between these 2 clusters. We have the cluster on the left in blue of 2 points, we have a cluster on the right of 3 points, and we have these 3 methods: single, complete, and average. The single linkage looks at all the pairs of points between the 2 clusters. You know what? Yeah, okay, that's fine. And identifies the shortest of those lengths. And that is the single linkage. That is the shortest distance between any pair of points between clusters. In contrast, complete linkage is the longest. So this point in the top left is the furthest pairwise point from the point on the far right. Every other pair of points is a little bit shorter. And average linkage does what you think. It looks at all pairwise distances for all these points and then takes the average. And using these different strategies to compute the distance between clusters gives you different characteristics on how clusters agglomerate into bigger groups. I think that's a good spot to stop the first video, and we'll come back and look at the mammal teeth example.